Good afternoon and welcome to this webinar of the EVACES Association for this webinar series. I guess everybody knows what is EVACES. This is not the first webinar that we do. Anyway, EVACES is the International Association for Experimental Vibration Analysis for Civil Engineering Structures. And it's actually a platform for professionals, researchers, stakeholders, people that are in general interested into vibration analysis and studies in civil engineering. EVACES is probably mostly well known for organizing the EVACES conference, which is designed to promote international cooperation and knowledge sharing in this field. EVACES also promotes, as an association, partnerships between academia and industry, which are very important for us, and also supports dissemination activities which are aimed at enhancing skills and knowledge of individuals involved in our field of study. So this is the EVACES board. Basically, it's made of colleagues active in the field of vibration analysis in civil engineering. The president is Álvaro Cunha, Professor Álvaro Cunha, because he was the chair of the past EVACES conference. And in the rest of the committee, you see myself, Professor Maria Pina Limongelli, Professor Gidang, and Professor Pierfrancesco Giordano. Myself, because I will chair, as I will tell you, the next upcoming conference of EVACES. EVACES Association is very active in promoting the activities that we do through social media and a website. So this is the website of the association. This is a screenshot we took some time ago. Actually, if you go on the website now, you have the QR code on the right. You will find EVACES 2027 on the top as the page of the upcoming conference that will be held next year. And of course, in the website, you'll find information about events, past events, news, and so on. We also have a LinkedIn page, which I invite everybody to follow. It's a very active LinkedIn page. So if you want to stay in contact and touch with all updates from EVACES, this is the right way to do it. We also have a YouTube channel. This webinar, together with other webinars that have been organized recently by EVACES, are on the YouTube channel, and you can see them at any time. So I was saying that EVACES conferences are the most important activity probably that the association is organizing. So they started in 2005 in Bordeaux, in France, and then there was a series of events, very successful events. There was Porto 2007, Wroclaw 2009, Varena 2011, Oro Prieto 2013, Dübendorf 2015, San Diego 2017, Nanjing in China 2019, Tokyo 2021. This one was unfortunately online due to the pandemic outreach and then outbreak, and then Milano 2023, and last one, very successful event in Porto in 2025. On the right, you see a very famous view of Porto, and the chair and co-chair of the conference in Porto were Professor Álvaro Cunha and Professor Elsa Caetano. Just to give you an idea of the participation to this conference, the proceedings of the conference are available in lecture notes in civil engineering in Springer. In total, there were 378 participants from 44 countries all over the world. 314 accepted papers. There were 45 special sessions, 6 plenary keynote lectures, and 5 industrial plenary presentations. Regarding the next conference, I'm very honored and glad to inform you that the EVACES 2027 will be held in Perugia and organized by myself and a group of colleagues at the University of Perugia from September 7 to September 10, 2027. Here you see a picture of the main square of the city of Perugia, which is a very beautiful ancient city in central Italy, in the Umbria region. And I will be the organization will be by myself as chair, and as co-chairs I will have 2 distinguished colleagues and friends who are Professor Carmelo Gentile and Professor Antonina Pirrotta. Just quickly, I will not show the whole video. This is an animation of the presentation we gave in Porto in 2025 to propose the candidacy for Perugia in 2027. This gives you an idea about the city, which is an historical university city with 2 universities and an academy for fine arts. So it's really a city full of culture, history, dates back to the Etruscan period and then Roman period and Middle Ages up to today. So it's very ancient, but still vibrant, very vibrant city in what we call the green heart of Italy, which is the Umbria region. Here you see some spots, important spots of the city, like the Etruscan Arch, the most important Etruscan monument in the world. We have very important paintings like this one by Raffaello. We have an aqueduct that is Roman. And then we have several remains from the Middle Ages, like important towers, like the Shiri Tower that is known to this community for being the case study of several research papers by our group. National Gallery of Umbria, and very important and iconic fountain of the city dating back to the Middle Ages. So this is a little bit about the city and about the venue. Most of the activities will be in this building, which is the main building of the university, the rectorate. University of Perugia is a university that is more than 7 centuries old, one of the most ancient universities in the world. This is about the team, a little bit of logistics, but you will find all this information in the future. This is where we will do the plenary lecture in the main hall of the university. And these are other rooms where we will organize the sessions. And okay, here I give you a glimpse of what is the city of Perugia, with many discoveries you will do also from a cultural point of view. All right, so the scientific committee members are reported in this slide. So we have distinguished colleagues from all over the world, very active in vibration analysis, structural health monitoring, and so on, structural dynamics, linear, nonlinear dynamics, and so on in civil engineering. It's very important for the association to strengthen collaborations with industries. So we have industrial committee members that you see in these slides, which are always supporting, and we are very grateful to them, the activities, scientific activities of the association. So today I have great pleasure to introduce you to this webinar, which is entitled Monitoring Breach Vibrations Using Spaceborn SAR Microdoppler. So it's a very interesting topic of remote sensing, so sensing from satellites, where many people are today, let's say, familiar. Not many, but at least, I mean, there is, it starts to be well known, the use of satellite radar interferometry for displacement monitoring over the Earth, and also in buildings and infrastructure. But very few people know that it's possible today. I mean, it's pioneering, but it's possible today to use this kind of data also for doing vibration analysis, which is the focus of EVACES conference. So this is really something that is, as far as I understand, really at the very beginning, but to me sounds pretty interesting. So the speaker that will tell us about this, research and technology is Daniele Zonta, Professor Daniele Zonta from the University of Trento. Daniele, he's a full professor in Trento, and he also has a courtesy appointment at the University of Strathclyde in UK, as well as a courtesy appointment in the Photonics and Nanotechnologies Institute of the Italian National Research Council. He obtained his doctorate in structural mechanics in the University of Bologna in 2000, and he was working for a while in the United States as a postdoctoral researcher at the University of California, San Diego from 2000 to 2001. He's been recently visiting scholar at the University of California, San Diego, in Princeton, University of Michigan. He founded and led until 2019 the Center for Intelligent Infrastructure at the University of Strathclyde. So Daniele's research encompasses infrastructure management, SHM, sensor and information technology, decision making, all applied to civil infrastructure. Maybe he's missing Bayesian inference, but probably is involving this into the topics I have mentioned. He's well known for Bayesian inference as well. Much of his work is carried out in collaboration with major European infrastructure operators, and like the Italian railway network, Italian highway company, and so on. Dr. Zonta is a council member of ISHMI and he's a senior member of SPIE. He serves on the board of directors of IASCM and chairs FIB-TG 3.5, which is Committee on Forensic Engineering. He's also a member of CHEN TC 250, Structural Eurocodes, and other boards. He chairs the annual International Summer School of Smart Materials and Structures and regularly organizes conferences, mini symposia in the field, in our field. And he's also editorial board member and reviewer for leading journals in our field. He's co-founder of Intelligent Infrastructure Innovation, which is a startup of the University of Trento. And it was awarded in 2014 of the prestigious SHM Person of the Year, which is an award given by the SAGE SHM editorial board. And of course, he's well known for his papers. He has published over 200 papers, really well known and well cited in our field. So with this, I think I can thank you all for your attention in this introduction to the webinar. I stop sharing my screen. I just give you a technical information. When it will be time to make questions, please use the question and answer that you find on the bottom right, three dots. Then you open and you find, in Italian is domande e risposte, or question and answer, depending on the language of your system. And please type the questions there. At the end of the webinar, I will read the questions, pose the questions to the speaker, and the speaker will answer. Okay? So, Daniele, thank you very much. I now leave the floor to you.
Thank you very much, Filippo, for your nice introduction. Yes, as you mentioned, today we're going to talk about SAR, satellite SAR monitoring, but in a different way than the usual. We're talking about the use of SAR for vibration measurement, in particular in bridges. Okay. So I think most of us is familiar. Before starting, let me just acknowledge the contribution of this work. So this is a collaborative work that involved the University of Trento, the University of Strathclyde, the Houston University, and the ESA, the European Space Agency. And I would like particularly to acknowledge the contribution by Alessandro Lotti, that is preparing his PhD in this topic and gave me and prepared this presentation actually. So most of us know that SAR, the meaning of SAR. SAR is an acronym for synthetic aperture radar, and these SAR sensor, these radar sensor, are active sensors that are usually mounted on satellite that orbit around the Earth. And they take measurement of the air using the wavelength of the radar. Radar works and operates in the microwave spectrum, meaning that the wavelength length is in the order of say the millimeter or the centimeter or some centimeter, and depending on the wavelength, so we distinguish different bands of radar. So the most used for the ground observation application are the band L, that has a wavelength between the 15 and 30 centimeter, the S 7.5 to 15 centimeter, C 375 to 7.5 centimeter, and in particular for our application we use a lot the X band that work with the wavelength in the order of 2.534 centimeters. This SAR is essentially a radar sensor which antenna aperture is not physical but is synthetically achieved, simulated by the movement of the satellite around the Earth, and the satellite are orbiting around the Earth, following typically a north-south polar orbit, and the motion is ascending if we go south to north, or descending if we go from north to south. And because of the rotation of the Earth, they can typically observe any any location of the Earth as long as the Earth rotates. And there are different modes for operation of a satellite SAR, a spaceborne SAR. The most typical are the scan SAR, so is a wide coverage, which is made typically with a moderate resolution and with a swath width in very wide, in the order of 200 kilometers. Essentially, the satellite is scanning continuously the Earth's surface with a very low resolution, with a resolution in spatial resolution. These satellites that works in the way are, for example, the Sentinel-1, and the data that coming from Sentinel are completely free. You can access the website and download the radar images that is recording. Another way of acquiring data is the trip map. Trip map is a balance between resolution and spatial coverage. Essentially, the satellite is again used for scanning the surface, but with a much higher resolution. Normally, the swath width is in the order of 40 kilometers, and so image of the ground are recorded and are archived continuously over the Earth, and this is, for example, the way how many satellite missions are working, including the Cosmoclimed, the one for the Italian Space Agency. Then for specific application, some satellite mission allow the so-called spotlight operation mode. In this case, the satellite essentially focus on a specific location for a long observation time, and so over its passage it just cover a very small area in order to have a very refined, high resolution satellite image of a particular structure or a particular location of the Earth. And normally the size of this image is in the order of 10 kilometers by 10 kilometers. So there are many satellite missions that are operating around the currently operating, and they distinguish about the band of the satellite, so the revisit time, the operation mode, the resolution, and the temporal coverage, so how long they are being observing the Earth. For example, Sentinel-1 that operates in band C has a revisit time of 12 days, so we can have a picture of the same location every 12 days, but with a resolution that is relatively low for civil application. For example, it's in the order of 540 meters, and they are operating since 2014, so we have data since that year. Other example are, for example, the TerraSAR X, so is the German space agency, or the Cosmoclimed that operates, that is from the Italian space agency. So both are working in X band, and they are normal revisit time in the order of 1 week or 2 weeks, depending on the particular time and the particular location, and with the resolution that are in the order of 1 meter. And we have image archived of this from this satellite starting from 2007. So other examples satellite that work particularly in the spotlight are Ambra or Capella. These are private companies that operate a satellite that work in the X band, and they normally work with tanking spotlight observation of the Earth with a swath size that is very small, so in the order of 5-10 kilometers, and this allows a resolution, spatial resolution, which is much better than 1 meter, in the order of 0.2, so in some cases 0.1 meter. And they are operating since 2018 for Capella and 2021 for AMBA. So how does it look as our imagery? Normally, satellite mounts a different type of sensor, and of course it also take optical images, so regular image of the ground. So, for example, if we focus on attractors, so here we can see an example of a renter image, which is an optical image. And optical images are very useful, but have some limitations, some constraints. And particularly, we can take them only during daylight hours, and they are very sensitive to the atmospheric conditions. In contrast, radar images are complex images that essentially does not require sunlight and are almost independent on the atmospheric conditions. So for them, the atmosphere is completely transparent. What we see from a radar image is something like this. This is, for example, the same picture of the Golden Gate Bridge in optical view and in radar view. And this is, for example, as we say, a radar image is a complex matrix, and the amplitude of the complex matrix is the so-called reflectivity. So it actually depends on how reflective is the point on the ground to the radar wavelength. So this is typically what are reflecting point are metal materials, so like cables, guardrails into bridges, and in general reflective surfaces. And the intensity, the color that we see here, the intensity of the color is essentially the intensity of the reflectivity. So the more is reflective, the point on the ground, and the lighter we can see here on the image. And then the phase of this complex signal is essentially the phase, is the delay of the backscatter signal, and this is a quantity that we can if we look at the picture per se is not useful at all, but is useful for us to understand what is the distance between the satellite and the location on the ground. And let us explain a little better how does it work. So if we have a point on the ground that moves, and we take two separate pictures at different time of the same location on the ground, so the two pictures will result with a difference into the phase, and this change in phase is related to the change in distance to this simple equation. So the change in phase in the radar signal is 4 pi divided by lambda, where lambda is the wavelength of the radar, times the difference in distance. So if an object moves, essentially we will observe a change in phase of this object. So the logic of this is that to use interferometry, so make it a difference between two radar images in order to calculate what is the change in phase for each of the point which is reflected on the ground. In principle, yes, the phase is a little bit more complex, the process, because the change in phase that we observe not only depend on the motion of the object, but also depend on, for example, on the topographic condition on the ground, on the atmospheric condition, and depends also on the noise. But if we use this method in interferometry, so we make a difference between two measurements made in the same conditions, so most of these disturbances cancel out, and we are able to see directly the change in displacement. Okay, so if an object change position in time, we will be able to observe it, and in general, as long as its motion, its displacement, is not bigger than 1/2 of the wavelength of our radar. So, for example, if we're using a band X that works, for example, with a wavelength of 3 centimeters, so we are able to observe directly change in displacement that are smaller than 1.5 centimeters. If not, if the displacement is bigger, so we are going to have an ambiguity in phase. So we will record the same phase and we are not able to distinguish which one of these signal which one of the displacement is the correct one. Okay, how does it typically use this technology? This is normally used when a interferometric SAR using a technique which is also known as multi-temporal INSAR. So the logic is to take a lot of pictures of the same location over the time and then compare the different picture to a particular time, to a matter image. And by having multi-acquisition, we can, for example, observe what are the points that are always scattering over the time. So these points that scatter consistently, so continuously, are called persistent scatters. And this is a particular point that are recognized in every image over the time. Perfect. Once we recognize this object, we can also look at the displacement of this object by observing the changing phase from the different image over the time. And based on that, we are able to calculate the displacement of this object and the velocity that will change the location of this displacement. The typical assumption that is made for analyzing data on the ground is assuming that that the motion of the object over the time is constant over the time, so it's slowly displaced over the time. And by using this, and maybe there is a dependency on the temperature, and by fitting all the phase data over the time, so we are able to see what is the typical displacement velocity of the object on the Earth. So the quality of this fitting is calculated to a metric that is known as temporal coevents and effectively tell us what is, if it is credible or not credible, the number that we are extracting. So we typically extract from an analysis only the point, the persistent scatter that have a high temporal coherence that fit very well this curve. And in other words, the temporal coherence is the stability of the other phase measured on the PS of a multiple passage of our satellite. Okay, so by using this technique, effectively we can identify a number of reflective objects on the ground, and we can observe their displacement over the time, so the velocity whereby they slowly displace over the time. Let's sum up about the limitation of INSAR for statuary monitoring. INSAR, interferometric SAR, is used in statuary monitoring to observe slow motion of the object on the ground. So it's only effective with slow long-term deformation. So we're talking about millimeter per year. So that's what we normally observe, or at least millimeter per, at least some fraction of millimeter per day. So this is the order of magnitude of what we normally can observe to this technique. And this requires multiple acquisition taken at the different passages of the satellite over the same location. And because of this, we have obviously a limited temporal resolution that depends on the passage period. So depending on the satellite mission that we are using, this is typically in the order of, in the better case, 1 day or 1 day, and typically more day, and most likely 1 week or more. So this is a technique that is very effective for measuring displacement, very low displacement of our structural element or our bridges, for example, but it's completely useless if we want to take the vibration of our bridge. So the objective of the rest of the seminar is essentially to try to answer to this question. Can we use a satellite SAR for recording vibration on a structure on the ground or a bridge, for example, on the ground? And particularly, is it really possible to take a measurement of vibration using a SAR? And if it is possible, how accurate is the measurement? And the last question is, okay, assuming that we can do that with a level of accuracy, so will be possible today or maybe in the future to perform a model testing, a model and a model extraction of the characteristic of a bridge on the ground using the satellite. So replace the typical operational model testing that we are currently doing by displacing sensor on the bridge by just one or more observation from the satellite, so with no contact at all. Okay, let's talk about talk about the possibility of using or recording vibration with SAR. The answer in general is yes, in principle is yes, because we can exploit the so-called Doppler effect that we have into our satellite image. And let's explain it a little better. So when a target, we normally, when we analyze and we recreate a radar image, radargram, using our satellite, the assumption is that the objects on the ground are fixed, that they do not move, or they move very slowly. And but if during the passage of our satellite, our object is actually moving with a velocity, okay, we will experience the so-called Doppler effect. The Doppler effect is a shift into the frequency of our signal that depends on the velocity of our object on the ground respect to the light of sign or the direction of observation of our satellite. In other words, if our object is moving toward the satellite with the same, so we will observe, or against our satellite, we will observe a change in frequency of the returning signal to the satellite. What is the practical effect of this? If an object is moving with constant velocity, what happened in the radar image is that it will appear shifted into the space of a quantity x that depend on the velocity of the object. Let me make an example here. So this picture here, for example, show the optical image of a port and here this is the reflective map of the same port, and this is a zoom of the same thing, and we can see here the radar image of a boat that is moving in this direction here. The original location of the boat can be inferred by observing the wave that he left behind. Okay, but we can see that that actually the location of the boat is that the position into the image is shifted of many meters toward the direction of movement of the satellite, to the azimuth direction. Okay, so because it has a velocity, because it's moving with a certain velocity, so this object appear shifted toward the azimuth direction. Okay, so this shift in space depend on the velocity, is proportional to the velocity of the object, then depend on the distance to the satellite, and it also depends on the velocity of the satellite. This quantity is a constant, so it's essentially, it is just a quantity that is proportional to the velocity of our object. So by observing the displacement, the shift, we can understand whether an object on the ground is actually moving, Okay, so what happened if a satellite, instead of moving with a uniform velocity, is vibrating? So this is an example. For example, this is a reflector. So it's an object that reflects very well the radar signal that is moving up and down. Sorry, that is moving up and down. And what are we expected to record on ground? So because it's change velocity over the time, so what we observe on the radar image is on the side image is this smear. So this is the defocus of the image. And so we see effectively the object in different location at a different time, which correspond to the different velocity that has our object doing the vibration. And the maximum displacement correspond to the maximum velocity that the object has on the ground. And the nice thing is that even the actual displacement of the object is very small, so it's the order of centimeter. Because it's moved with a velocity, it actually displays many meters into the picture. So it's very easy to observe it, even if the resolution is not too high. Okay, so this is a very interesting thing. And but the question is, okay, this picture, by observing this picture, we understand the object is vibrating, but we cannot reconstruct its actual vibration unless we analyze the image using this method. Okay, this is the full radar image that has been generated by the overall observation of the object doing a spotlight operation. And let's call T time of aperture, so the total aperture time, the total observation time, whereby our satellite observed the same location doing its passage, its single passage. And so the image that we record is something like this. What we can do is to, decompose this image, this radar image, to segment essentially the full image into sub-apertures, into sub-images. So just use one part, one sub-aperture of the observation of the satellite in order to reproduce a sub-image, a segment of image. And we will see an image that has a much rougher resolution in space, but is more focused into the location of the object of the time. And so if we repeat the operation for different subaperture, so we get a different image, and on each of these subaperture, we can identify the most reflective point, and this most reflective point is essentially the peak of the reflectivity. And if we trace the peak of reflectivity over the time, we can somehow reconstruct the movement of the object over the time, reconstruct the velocity of the object over the time. So the general method that we want to use, and that we can in principle use to reconstruct the time history of an object. The time history is the velocity of the object toward the light of sight, toward essentially the direction of the satellite, of observation of the satellite. Okay, so we started doing an experiment in order to verify the feasibility of this method. So we just put ourselves in the best possible condition. First of all, we had an isolated object that is made by a corner reflector, so it's essentially a structure that is a prism, effectively, that reflects very well the radar signal. We used high resolution amber acquisition with a resolution in the order of 20 centimeter, and then we put ourselves in an open field, so with no other disturbance around. So that's the perfect condition to do this test. These were made actually in two different locations. One is in a field close to the University of Trento, and our is in another field in the Glasgow Green, closer to the Tactile University. And we repeated the test in different conditions with a single harmonic oscillation and constant amplitude, with single harmonic oscillation and modulated amplitude, with the superposition of different frequency, and with the linear sweeps. And so the radial velocity also changed from 160 millimeter per second to down to a limit of 1.5 millimeter per second. This corresponds to vertical displacement, from 5 millimeter to 0.2 millimeters. So the frequency is changed from 1 to 4 Hertz. And this is, for example, an example of our experiment. So this is, for example, a picture of the Funke rare image taken in a particular test, and here we can see very well the smear of our signal. And if we apply the algorithm that we've seen before, we can see here the sequence of the subaperture pictures. And if we track with the maximum reflectivity in this picture, so we can reconstruct the displacement using the formula that we have seen before. And you can easily see that each subaperture has the shorter is the subaperture, the lower is the azimuth resolution, so the lower is the quality of the picture, and so the lower the resolution we can achieve in velocity from this. So there's some kind of trade-off on how good is the resolution and how many samples we can get in our signal starting from the same full image. Yeah, some of the results that we get with this preliminary test. So this is a very comfortable test where we used a very high amplitude in the order of 50 millimeters with a frequency of 1 Hertz. And the velocity amplitude in this case is in the order of 95 millimeter per second, so it's relatively high. And we can see in black the ground truth, so the truth signal taken with a sensor on the ground. And with the blue and red, we can see the rough and interpolated signal that we achieve by analyzing the data from the satellite. And we can see that the match is pretty much good. And so we see very well that the satellite can track very easily the actual response of this vibrator. And the FFT is also very good. We can easily identify the peak of resonance. If we use a different, this is another signal. Here the amplitude and velocity is slightly smaller, the frequency is higher, and we can see that the match is not as good as before, but we can still see that the phase is captured perfectly. The peak recorded is very close to the real one, and so it's very satisfactory, this signal too. And we test a different condition. This is, for example, and a modulated frequency into time, and we can see how the satellite track very well, so the change, well, reasonably well, let's say, the change in amplitude over the time, and this is good for this signal and also for this EVACES-IA. See, this is an amplitude of 58 millimeter per second. This is a signal with a very small amplitude. It's only 3 millimeter per second, and you can see you can still recognize reasonably well the motion of the signal on the ground. So these results are very satisfactory. So we, to some extent, we demonstrated that it is possible to record the motion of a vibrating object on the ground. And this was possible to the extent we established that we can quite clearly see the motion, the vibration of the object, as long as the radial velocity is in the order of 1 millimeter per second. I mean, we have good result if it is equal or bigger than 1.5 millimeter per second. And of course, interaction quality and the match between the real signal and the satellite recorded signal increase significantly with the velocity of oscillation. So it also increases either we increase the amplitude or we increase the frequency of vibration of our object. And again, we have this trade-off between the resolution that we can get and the number of samples we can get. So in order to have a good velocity resolution, we need to have relatively long aperture times, subaperture times. And so we need, in order to have a finer temporal resolution, we need to have shorter aperture times. So this is trade-off. If we want, we have to find the perfect match in order to have a reasonably good signal in amplitude. We can track over the time the signal, and at the same time we have a decent velocity resolution of the object. Of course, we can do some trick. We can do some overlap between the different subaperture. But in short, this preliminary test demonstrate that we can actually measure vibration using satellite. We can see a vibrating object on the ground, and even if the velocity is relatively small, so in the order of millimeter per second, which is the same velocity that we're expecting in some cases from building or bridges that are on the ground. So at this point, the real question is, yes, we can do this, but what happens if we try to apply this to a real structure? So we try to do this test on a real life bridge. The case study chosen was the South Portland Street Bridge. Is a pedestrian wrought iron suspension bridge. Is an heritage bridge built between 1851 and 1853, and is one of the landmarks in the city of Glasgow. Is a 128-meter long suspended bridge. It is supported. The chains of this bridge are supported by two sentinel towers that are 10.25 meters tall, and the chain support the deck of the bridge with 77 iron hanger per side. It is a pedestrian bridge that can be easily assessed, and we choose this particular bridge because it's easy to assess, first of all, and because we were expecting a level of vibration that is in the order of magnitude we hope to see from the satellite, essentially. So to start, we instrumented the bridge with a number of accelerometers in order to have a reference ground truth for the satellite measurement. We used two different configurations, in both cases with 10 accelerometers. So the first one with all 10 accelerometers displaced vertically, and this was made particularly to carry out some preliminary dynamic identification, just to do a regular model testing with the traditional vibration-based method. And the second configuration was instead used in order to have a vectorial response of the velocity in each location in order to compare directly to the vector or to the velocity in the light of sign that we are expecting from the satellite. Okay, and these are some examples of the signal recorded by the accelerometers. Of course, we did many tests, also to characterize dynamically this bridge in order to extract the frequencies and the mode shape using an operational model analysis techniques. So we acquired for several times long records in the order of 15 minutes, and we can see here some example of the vertical and the horizontal response, also the response in the different location. And these signals were used again, first of all, for the performance operational model analysis. Was made with 20 minutes acquisition from 10 different channels, and this is the FDD, for those of you who are not familiar with that, but I presume all of you are familiar with that, essentially consists in extracting the single values of the different cost correlation spectrum, and the first single value is the one where the peaks normally represent, or peaks normally allow to identify the frequency of your signal. And by using the FDD, we were able to extract 9 different mode shapes that are very clear, are very clean, and are reported here in this slide. Okay, this was very useful in order to interpret the data that we're calling from the satellite. And then we made some satellite acquisition by acquiring at the same time with the accelerometers. These are, for example, two examples of acquisition. So the acquisition number one is a relatively short acquisition of 7.50 seconds, and acquisition two, and this allows an azimuth resolution which is in the order of the 20 centimeter, where acquisition 2 was an acquisition tackled in order to be particularly long. Particularly long for a satellite means something more than 10 seconds, and so the maximum virtually possible will be something in the order of 20 or 30 seconds. This is a 16 second long and allow a resolution of 8 centimeters. Again, we can see here the picture of the same South Portland Bridge in an optical image and in the corresponding radar image. And just by examination of this picture, we can easily recognize the location of the different angles of the bridge. And this means that it's very well visible from the satellite. This is, for example, acquisition one, and this is again the reflectivity map of acquisition one, and this is a zoom image where again we can see very well, we can separate very well each of the angles of the bridge seen from the satellite. And we can use the same algorithm in order to generate different superpertures, and this is what effectively we achieve. So we can see that the single angle is mirrored, but we can see that it moves left and right, and so in the direction of the azimuth. And by tracking the peak of reflectance of this angle, we can understand whether our bridge is moving vertically. And this is some of the signal that we achieved. So this, for example, one of the signal in black is again the ground truth recorded to the accelerometers, and in blue we can see what is the signal reconstructed to the satellite observation. And we can see that more or less the amplitude is very, very critical, is really at the limit of the capacity of the satellite. We are in the order of 1-2 millimeters per second on amplitude. So the RMS error in amplitude is relatively big, is in the order of 0.7 millimeters per second. But we can see that the satellite can capture perfectly, for example, the phase of the response, and more or less the amplitude is tracked in a reasonable way. In terms of spectrum, the spectrum can identify the maximum, the peak of the spectrum is very, very close to the peak of the spectrum that we achieved to the same accelerometers. Okay, one limit of this method is, of course, related on the time of observation. For example, if a time of observation, the resolution in frequency that we can achieve is the inverse of the total time of observation. So because we have observed this bridge for just a little bit more than 7 seconds, the resolution in frequency in this case is 0.14 Hz, which is good or bad depending on our applications. In our particular case, yes, it's good, it's not good, but we understand that where in the satellite signal we see one single peak, in the reality, this is a superposition of different modes that we know that are there because we did model testing, but if we just observe from the satellite, maybe we are not able to separate the two. Let's say that this is the quality of the signal that you can achieve. The correlation, the percent correlation in time is in the order of 0.66%, and the correlation in frequency is much higher, in the order of 90%, which is very good. These are our signal achieved in the same bridge doing the same acquisition. And you can see that the quality of the signal is similar. They are not perfect. The error is still in the order of the millimeter per second, but you can easily track the vibration, you can easily track the phase, you can easily track the frequency of vibration of our signal. This is the acquisition number 2. In this case, the acquisition is much longer, so it's in the order of 16 millimeters, so the resolution in frequency is much better. It's 0.06 Hz, and you can see that in this case, you can capture much better the different peak, and you can separate much better the resolution peak. And okay, so in terms of capacity of reconstructing the time history, what we can say is, yeah, the satellite can track the time history, but with this limit in the resolution that you can get, the velocity resolution you can get, which is in the order of the millimeter per second. That said, the spectrum is reasonably good, and you can recognize in your spectrum the frequency or vibration, and the phase also is correct. Given that, so what we can conclude is that by using the satellite, it's like using, you know, a noisy sensor, a sensor that have a noise in the order of the millimeter per second, and by observing our tractor, by acquiring our sensor for a very limited time, which is in the order of 10, 20, maybe in some cases 30 seconds. Okay, so the limit that we have in the model extraction from the satellite are the same limit that we would have from a sensor that is very noisy, and when we have a limit in the time of observation. It's like as we have allowed to leave our accelerometers only for 40 seconds, and from this limited measurement we have to make to extract the model characteristics of our bridges. Okay, so how can we say what can we get from this signal in terms of model extraction? And okay, we can, for example, perform FDD of the same of the time history recorded from the satellite, and compare to the corresponding time history recorded from the accelerometer at the same time, and we can compare the two things. We can apply an FDD exactly as we did from the longer signal recorded by the accelerometer, and this is what we get. Effectively, the single value is very similar in terms of frequency content, and we can recognize the location of the dominant frequency at the time of observation. And again, if we're using a long signal, the resolution in frequency is obviously much better, and we are able to decompose the signal. We can recognize, we can decouple the superposition. So, and so can we identify the frequency of the dominant vibrating frequency of the bridge? The answer is yes, we can do that. And can we extract the mode shape? In principle, we can do that, but the quality of the mode shape extraction is relatively poor because of the limit in the accuracy of the signal. What we can really do, however, is to recognize the mode shape. If we more or less have an idea of how are made the mode shapes of the turtle, we expect how they are made, we can use this information for model recognition. And so by using the Mach value, for example, for this signal, we recognize that this peak correspond to the mode shape for this particular mode shape, because the frequency is much closer to this, and the Mach is also closer to this. Okay, so in conclusion, let's conclude what we can. Let's try to answer to our 3 questions that we answered before. So, can we measure total vibration using satellite SAR? And the answer is yes. So with SAR, we can measure vibration in terms of velocity, and the velocity that we record are consistent with the ground truth benchmark. How accurate is the measurement? The measurement accuracy in the order, given the different tests made, in the order of 1 millimeter per second. So this is the limit that you normally can get with a SAR with a wavelength in the X band. will it be possible today or in the future to perform a model testing from satellite and replace the satellite to the traditional ground technique? And the answer is, it depends what you're interested to. If you're interested just to extract the dominant frequency of vibration of the bridge at that time, in principle, yes, you can do that, but with some limit. The main limit is the observation time. So the resolution in frequency that you can get is the inverse of the observation time. The maximum observation time is potentially, possibly, up to 30 seconds. So the beta resolution in frequency you can get is 0.03 Hertz, effectively, with the current technology. And also, the status must vibrate according to the dominant frequency at the satellite species. So you have to be lucky enough that your status vibrate with this frequency. And effectively, using the SAR is like using a very noisy sensor installed on the sensor and to record the signal just over a limited time, 20 seconds, 30 seconds maximum. So the same limit that apply to a sensor on the ground apply also to the satellite. And this limit essentially say that, yes, in principle, you can get the frequency, you can recognize the mode shape, and because you can recognize the phase of your point, but probably you cannot do with this technology a proper model extraction or a model extraction with enough accuracy. So it cannot really replace the ground. Is there space for improvement in the future? Yes, there is space for doing that. First of all, we can work on the reflection of our signal. We can try to use longer acquisition by tracking differently the satellite, and probably you cannot do much more with the current satellite mission that are orbiting. You can improve also the algorithm for extraction, but really in the future, yes, we expect we can do much better if we design the future mission with the appropriate sensor that are made for recording the vibration. For example, now we work, the satellite currently work mainly in band X, but we were using band K, KM, for example. The vibration will be much easily recorded by a satellite. Okay, so I thank you for attention, and again, I want to acknowledge the contribution of the people that worked to this work, and particularly to Alessandro Lotti, that is the first author of this paper that I recommend you to read. There are all the details on this work, and that is among the other, I want to mention Carmine Clemente and Pietro Melillo and Enrico Tubaldi that gave a contribution to this work. Thank you for your attention.
Thank you, Daniele. Thank you very much. Really very interesting talk. Thank you also for being perfectly on time. We already have a couple of questions in the question and answer spot. So I will read the first one. I also have a question, but I will leave it at the end. So Asmit Roy Burman is asking, do we need to use a fully focused SAR image, or we can use just the azimuth focused product to extract the vibration? If we can separately use azimuth focused and range focused products separately, can we extract the vibration in two different axes? This is the question.
No, because the vibration, I mean, the point is that the only vibration you will see will be the vibration in the light of sight. Okay. So in the same direction of observation of the satellite. So is focusing on the two directions will make no difference.
Okay. Actually. Thank you.
Ricardo Lewis is asking the question. Yeah. But yeah, it's the question if you can get a vectorial.
Yeah, exactly.
The answer is no, you can get only the velocity in the light of sight.
Right. Same as happens in SAR for the displacement in traditional static. Exactly. Yeah.
Well, but it's different from interferometric SAR because you can use two different satellites.
Right.
You get the vector, but yeah, you cannot.
But in both cases, you get the displacement component.
In principle, you could do that by using two satellites at the same time. And in principle, you can do that with some mission, with AMBA would allow in principle that, because there are many satellites but you have really to, organize a tasking that is very complex. Yeah,
Right.
and is and very expensive also.
Okay, thank you.
Normally the cost of an ultra-high resolution image is in the order of $3,000-4,000. So that will be the cost effectively of this observation, and an observation of 10 seconds, in the order of 10 seconds, something like this. And a more complex tasking is more expensive, of course. Yes, you can do for research, but if you need for commercial applications, they're being very expensive. So today, with today's technology, maybe in the future, will be much easier to do that.
Riccardo Liuzzo is asking, says, good afternoon. Thank you for the very interesting presentation. Do you think that the limitations that you highlighted in the conclusions could be addressed by new developments of this technique, or they are all related to satellite characteristics? Also, do you think that data fusion with information from other monitoring sources could help in getting better results?
Yeah, okay. We can answer this question. Oh, okay. The answer is both. Yes, there is some space for improvement with the current technology, and particularly is try to work on the tasking of the existing missions. It's something that can be done. Try to work on the peak tracking algorithms. Yeah, it's something on the. That's also something that can be improved, but of course there is a limit on that. If the resolution is in the order of the pixel resolution is in the order of the 10, let's say it's 10 millimeter per second. You can break in 10. You can, if you're good, you can break in 20 or 30. But at some point there is a limit.
Right.
So the sub-pixel tracking can be improved, but in the end there are some limits. So we empirically we observed that acquisition are possible, and recording are possible is very empirically if we are on the order of the millimeter per second.
Okay.
Below the millimeter per second, we start having too much noise to get something reasonable. The limit is principally in the wavelength of the radar. So because we're using an X band, right? So we're using an X band, that's more or less the noise that you get. If we're using a different band, for example, the band, band X means 2-3 centimeters, 20-30 millimeters of wavelength. If we use a different band, for example, the band K, band KM, for example, the KM is in the order of 5 millimeters. It's the same band that people are using from ground radar, for example. And ground radar, of course, used for vibration. So the IBIS, for example, using that wavelength. But these type of sensors are not currently mounted on the missions that are available. But if there was, of course, the quality of the measurement will improve proportionally, inversely proportionally to the wavelength.
Right.
So, the quality. The resolution is proportional to the wavelength, effectively. So there is a lot of space for doing this. And also the new mission could be redesigned for different tasking possibility. The other big limit is the observation time. It's probably the biggest limit.
The main
limit. Yeah. Because this even the point is, let me go back to the tasking, to the operation modes. Yeah. So the operation mode you need to use for vibration measurement is the spotlight. So the spotlight consists effectively in changing the line of observation of the satellite while the satellite is orbiting over your object. But there is a limit to that because the velocity of the satellite cannot be changed and will not be is not changeable even in the future because that's really depend on the orbit elevation.
Right.
And it could be improved the way how we can observe the same. We can focus on the same area from the satellite. This will not probably change of order of magnitude the observation time, but it's possible that with some trick the future mission can observe the same location for a time that is not in the tens of seconds, but in the order of minutes, and that would be
great. I mean, minutes would change completely.
1 minute could be just a good thing.
But with what we have now,
1 minute is definitely possible without a big change in the technologies.
Yeah, but with what we have now,
well, we are now is 30 seconds.
30 seconds.
I
So
would say
basically,
AMBA is 30 seconds, is more flexible and very allow 30
relative
seconds.
terms, the error that you introduce.
I mean, you can use different techniques. For example, you can use two satellites that observe the same location in tandem. So one pass first, the other observes right after, and then you have to mix up the two signals, and you can do with 1, 2, 3 satellites. It's very expensive tasking now. Maybe in the future will be something completely normal and completely affordable for. So the point is, in principle, you can do anything. You can do that. Today is feasible, but something is feasible. Something is not feasible. Something feasible is very expensive. Something is feasible and can be done very in a cheaper way. Yes.
So right now, what is the range of natural frequencies of structures where this technology is more attractive? Because of course, in relative terms, your error becomes smaller for higher frequencies because you have a fixed resolution error. So higher the frequency, lower the relative error. So the thing is that, but then higher the frequency, lower the vibration amplitude.
Correct.
So do you have an idea of what kind of bridges, for instance, you can?
Okay, so we ended up with a formula because in the end, what make it, because you correctly observe that if in order to have high velocity, you need either to have you need high frequency, but you have high frequency, you need a short time aperture. As you have short time aperture, you cannot resolve in time the same problem. Okay. I mean, you can make a calculation on some assumption. In the end, what make a difference is the total displacement of your tractors. Assuming that your tractor vibrate with a uniform harmonic frequency, in the end, what make a difference is the maximum amplitude of vibration of your tractor. So these are techniques that presumably work well with the bridge that displays a lot, that displays many millimeters or centimeters doing vibration. I'm talking about the bridges that has a span equal or bigger than 50, 60, 70, 80 meters, or longer. Okay, so for this type of bridge, you can use it, or in principle, you can use it. And for smaller bridge, is something that has to be tried, to be tested.
Right. Yes. All right.
But again, all the limit is on the wavelength and the observation time. If we can make a shorter wavelength and longer observation time, in principle, in the future, you can observe you can really do a model testing from the satellite. Not in a short future, but in a medium.
There is for sure a lot of space for development.
Medium term future, I think
there is another question by Asmit Roy Berman. Can we really use shorter wavelengths like Ka? Because with shorter wavelengths, the effect of atmosphere will be more significant. So how could we address this?
Absolutely, that's an absolutely right observation. So in principle, yes, by using, Km is not that yeah, KM is still acceptable, KA no, evidently. But yeah, you have this problem, you have to sort this problem. I totally totally agree with this observation.
Yeah.
Yes, because you solve a problem, but you have another. Yes.
Right. One last question from myself, Daniele. So, from how much automation can you achieve in this process? I mean, how much manual analysis of the data is needed, and could we really automate this? Because if it's automated and you have the possibility of monitoring, several structures or different assets in a certain scenario, that makes the things very appealing.
No, absolutely. Yeah. And the answer to your question is I don't know today, because in order to understand what part of the processing can be actually automated, you need to test, you need to apply this. And we didn't make so many tests. I mean, and to apply means let's test your bridge with the ground truth, with a ground system recording, and at the same time with a satellite that record in ultra high resolution. Okay, so we didn't do that many times. So this is one of the few examples we did. We are going to do more case studies over the next year. And maybe I can answer you to this question at the net EVACES in Perugia.
Right. Exactly. You know that we have a lot of bridges that are under monitoring right now. So this is something.
Yeah, but you have to acquire at the same time the bridge. I mean, you need a bridge with a particular characteristic. You want to see that from the satellite, and you have to acquire really at the same time when the bridge is vibrating. So that is
right.
But in principle, and everything also, because I can overturn your question and say, okay, look, how much of the model of the operational model analysis can be automated today? And the answer is no, not everything, not 100% of that. Maybe extracting the frequency peak, yes, can be done, but you need to give some hint to your system and whatever. So it really depends on what you really want to do. If your task is, okay, let's track the frequency peak of your bridge, for example. This is something that you can do, you can reasonably do, and it can be easily automated. But if you want to, it will be possible in the future to extract mode shape. And the question is, can you do that today with with a NOMA on a bridge that you have never tested? And you say, okay, let's start this algorithm, and it is extract automatically by mode shape and completely unmanned. Not even today you can do with a traditional sensor system. I think, right? You need to put some information inside, right?
So thank you, Professor Zonta. It's really a very interesting topic. I think there are no more questions from the audience. At least I don't see questions. We have had quite a nice time today. So thanks again to the speaker, and see you at the next webinar of EVACES. Thank you very much.
Thank you, everyone, and have a good weekend.
Bye bye. Have a good weekend. Bye bye.